Let's work problem 55 on page 220 in chapter 8. Here's the problem in the book. It says a figure skater can increase her spin rotation from an initial rate of 1 revolution every 2 seconds, which is an odd way to put it, to a final rate of 3 revolutions per second. If her initial moment of inertia was 4.6 kilogram meters squared, what is her final moment of inertia, and how does she physically accomplish this change? So let's work this. Here we have the skater, her arms and legs, or his arms and legs or whatever, are extended out. Okay, and we have 1 revolution every 2 seconds as our angular velocity. And then our initial rotational inertia is given to be 4.6 meters per second squared. Now, if they bring their arms and legs in, then they are taking mass and bringing it closer to the axis of rotation, which decreases their rotational inertia. But since we're assuming this is a skater on ice, and we're going to assume that there's no net torque on the person. And if there's no net torque, if the net torque on the person is approximately equal to 0. Now, is it exactly equal to 0? No, there's a little tiny bit of wind resistance, a little tiny bit of torque with the skates. But in a problem like this, you just assume that those, at least in the short term, those are negligible. And so if the net torque is equal to 0, then, well, we know that net torque is equal to the rate of change of angular momentum. If this is 0, then delta L is equal to 0. There's no change in angular momentum, and that means that the initial angular momentum will equal the final angular momentum. Well, the initial angular momentum is the initial angular rotational inertia times the initial angular velocity. That'll be equal to the final rotational inertia times the final angular velocity. And now we can solve for this. We know we can say, all right, well, the final angular velocity is going to be the initial rotational inertia times the initial angular velocity divided by, I'm sorry, we want the other thing. We want the final rotational inertia divided by the final angular velocity. Well, this is given to be 4.6 kilogram meters squared. Now, the initial one of these is 1 revolution every 2 seconds, which is 0.5. Am I off screen? No, I'm on screen. Okay. Which is 0.5 revolutions per second, right? 1 over 2 is 0.5 revolutions per second. Now, some of you went ahead and changed it to radians per second. That's not wrong, but it's not necessary, because what's going to happen is we're going to divide by this final angular velocity, which is given to be 3 revolutions per second. So even if I change this to radians per second and this one to radians per second, that conversion factor cancels out as well. So you don't really need to bother with that. So anyway, the revolutions per second goes away, and you plug those values in. Is 4.6 times 0.5 divided by 3. And you get 0.7666, so I'm just going to round it off to 0.77 kilogram meters squared. Now, how does she physically accomplish this? Well, if she brings her arms and legs in closer to her body by bringing her arms closer to her body, and it can be her leg too. I mean, she has to have one leg down, right? But if one leg is out, you bring all the arms and legs closer to her body. She decreases her rotational inertia but increases her angular velocity to conserve angular momentum. That's kind of a long explanation. Basically, I think if you said, she accomplishes it by bringing the her arms and legs closer to her axis of rotation. Now, the reason that works is it decreases her rotational inertia, and to conserve angular momentum, that's going to increase her angular velocity by the same proportion. Because this product and this product have to be the same. And when is this true? When there's no net torque on the person. Okay? Let me come all the way up so we can see the whole thing. Any questions? Okay, that is all.